Bismillahirrahmanirrahim. Beginning with the name of God, the Beneficent, the Most Merciful. Today, the topic of our discussion is heteroskedasticity, case of non-constant error variance, where variance of ui is not equal to sigma square. So let's see what's the nature of heteroskedasticity. According to the classical linear regression model assumption, the disturbances ui are homoscedastic. It means they all have the same variance. So variance of ui should be equal to sigma square, a constant. But suppose the variance varies across observations. Then we have heteroskedasticity. It means variance is not constant over observations. So we can see at our left in figure A, variance of ui is equal to sigma square. It means the variance is constant throughout the distribution. So this is homoscedastic disturbances. At our right side in figure B, variance of ui is equal to sigma I square. It means variance is not constant, so the problem is heteroskedastic disturbances. Let's see one example. Average wage rises with the size of firm. Suppose the size of the first firm is 1 to 4, with mean wage is 3396 and standard deviation is 744. And the size of the last firm is 250 plus, with mean wages 4538 and standard deviation is 1310. So can we expect the variance of wages to be constant? Definitely not, because the variance increases as firm size increases. So larger firms pay more on an average, but also there is more variability in their wages. So we can say heteroskedasticity is more likely in cross-sectional data than time series data. So what are the reasons of heteroskedasticity? According to Gujarati, following are the main reasons of heteroskedasticity. Number 1. Error learning model. It follows the theory of learning by doing. It means as people learn more, likelihood of errors become smaller over time. So sigma square is likely to decrease. Number 2. As incomes grow, people have more choices about disposition of their income. So sigma square is likely to increase. Number 3. Improvement in data collection techniques may causes the sigma square to decrease. Number 4. It also indicates the outliers in your distribution. Your distribution may have some extreme high or low observations. So what happens when OL is played with heteroskedasticity? Beta 2 cap is still best being consistent. Beta 2 cap is still linear. Beta 2 cap is still unbiased. But the problem is that beta 2 cap is not efficient now because of the violation of minimum variance property. So what we can do? We can use GLS estimators in place of OLS estimators. So what are the consequences of using OLS when plagued with heteroskedasticity? Usually, TNF tests are likely to give inaccurate results. Since beta 2 cap is inefficient estimator, on an average, it overestimates or underestimates. So on the basis of that, we may draw misleading conclusions or wrong inferences because standard error of intercept will be too high and standard error of slope will be too low. Let's see how we can detect heteroskedasticity. Actually, detection of heteroskedasticity is not a difficult task. We can use formal methods and informally we can check that. Informally, we can check intuitively by looking at observations for possible outliers. And we can examine our residuals after running regression. According to Iqbal, we can do the following for the detection of heteroskedasticity. In two-variable model, plot squared residuals against the independent variable. So residuals should not be correlated with any of x or y. In multivariate model, do against different suspected x or against the predicted value of y, because predicted y is a linear combination of the x, and we can check through graph because it could show linear or quadratic relationship, because graphic plots provides clues about the nature of heteroskedasticity and how we can transform variables. We will use e-views for this, but first we'll do informal method. First of all, we have to open e-views. So just go to the start button and click that and write e-views in command line. So the e-views will automatically be open. This is the main screen of e-views. This is the main menu and this is the command line. So now we have to open our food file. I have already downloaded this file from the website. You can download this file from www.principlesofeconometrics.com. I repeat, you can download this from the website www.principlesofeconometrics.com. Now we can see here the inner window. This is the file window. eViews has the utility that it can provide so many files at a time because it provides graphical view. So we can open as many files as we want. For example, I like to open other files in the same window. So I'm going to open another file. Now you can see we have two files, and top of the menu you can see the name of the file. This is food file and this is X-rate file. So now I'm opening another file. So this is third one. Now another. So it's 4. So we can open as many files as we like. But here our concern is in food file. So we'll use food file. So I'm closing all other files. Now this menu is file specific menu of eViews. It is showing all of its detail. It means this file has 40 observations, and in the inner window we can see it is a C. C means it's intercept and it's a vector. But since we haven't done any operation right now, it is blank. The second one is food expenditure. It is our actual data file. So we can see the data here for possible outliers. Then we have income. So we can check for any possible outlier in the income. And the last one is residuals. You can notice here residuals is black now because when we run the regression, it takes our values from the regression. So let's start by running our regression. We have two options to run regression. We can directly do this by typing the syntax, or we can use quick menu, estimate equation, and then write your regression relationship. Food expenditure, then C is for intercept, and then income. Now I'll just click OK, the regression will run. Now you can see this is our regression result. And you want to check residuals, so you can check residuals right here. Now it has some values. Now we have to check residuals graphically, so we just have to click residuals. And this is the graphic plot of residuals, which is showing that as the income is increasing, residuals is also increasing. It means the variance is not constant in this. So there might be Some problem of heteroskedasticity in this regression. So we are going to save this. So equation 1. Alternatively, we can run our regression through command line. So just type ls food expenditure c income and press enter. So we got the result of regression. Right. So if you just analyze the standard error of intercept, it is too high, and the standard error of slope, it is too low. So it is possibly the case of heteroskedasticity. Now we're gonna save our residuals in one variable that's named e hat. So we're going to generate by the command genr generate e hat, and we are just setting this e hat equal to residuals. So it takes the residuals from the last regression run. Now you can see the variable has been created, e hat. Now we are going to generate another variable, that is food hat. So food hat will be equal to food hat equal to food expenditure minus e hat. Now we are going to generate our graph. So just go to quick graph and scatter. So here we are giving the variables on which we need graph. So the first one is income and e hat. So just go to line and shade and select horizontal left scale and give the data value 0 and press OK. Now you can see our graph. At x-axis it has income and at our y-axis has e hat. So this is a way we can use our informal method for the detection of heteroskedasticity. So one other way to see the dependence of the magnitude of the residuals on income, we can just plot the food expenditure and the least square estimated line against income. So how do we do that? Just click the income, then press control and click food expenditure, and then click food hat. Just press the right mouse button and open as a group. Now view, just go to graph and select the XY line and one X against all Y's. So there's a graph. Just press the right mouse button and select the option and select the symbols only. So it will give the scattered line. Now we can see the scattered line and the graph. So the magnitude is showing that the variance is still varying. So it is likely to be the case of heteroskedasticity. So in the formal methods, the first test is spark test. If we have any evidence of heteroskedasticity and we know the variance of the regression, so we can use our variance as a dependent variable against the independent x. But if we don't know the variance, as in most cases, so we can use the squared residual as a proxy variable. And we can run our regression by using the squared residual against the independent x variable. And if beta 2 is significant in this regression, so it means this regression has a problem of heteroskedasticity. So let's apply the park test to our regression. The first step, we have to run our regression. So just go to command line and write ls food expenditure intercept then income and press enter. Now we got the result of regression. So the second step, we have to generate a variable. So I'm going to generate by using the command generate GENR squared residual is equal to residual square. Now we can see here, this is the new variable, residual square. Now we run our regression on this to check the relationship between residual squares and independent variable. So let's run the regression. Ls residual square intercept and income. This is our regression result, but we have to take log before running our regression. So now I am going to run regression by taking the log. So just write the command ls log of residual square intercept log of income. So this is our desired result. Now here we can see here the t statistics of log of income is significant in this regression. So it means we cannot reject the null hypothesis of heteroskedasticity. So here this is the evidence of heteroskedasticity because our independent variable is significantly correlated with the squared residuals of our regression. The second test in our heteroskedasticity testing lot is cluster test. This test is quite similar with Park test, but in this test we use the absolute values of residuals rather than its residuals square. So the form of regression may be different from the Park test, maybe because in this test we can use square root of x or 1 upon x. The method is same if the t values are significant, the same as in Park test, so we can conclude that the data is plagued with heteroskedasticity. So let's apply the Glaser test to our regression model to test the heteroskedasticity. As a first step, we have to run our regression model. So let's run the regression. ls food expenditure 3 income. So we got the regression result here. Now we are going to generate a new variable that will take the absolute value of residuals. So we are going to generate absolute residual and setting the absolute value of residuals. Absolute residual. Now you can see the new variable has been created here, that is absolute residual. Now we're going to run this residual against our independent x variable. So let's run the regression. ls absolute residual c income. Now we can see the slope coefficient of income is significant in this case, so it means it is confirmed by the Glaser test that our regression has a heteroskedasticity problem. So another test we use for testing of heteroskedasticity is Goldfield Quant test. In this test, we hypothesize that the order of the observation is rated according to the magnitude of the x. As a first step, we sort the values of x variable and omit some observations from the middle. Then we divide observations into two groups, one with low values of x, and run the regression on these samples and get residual squares. Then we run the regression on other group of high values and get another residual squares. Then we calculate the f statistics. If our calculated f statistics greater than the f tabulated, then we can reject the null hypothesis of homoskedasticity. So let's apply the Goldfield contest to our regression. So for this purpose, first of all, we have to generate a variable that will take the values from income. Then we remove some values from the middle and split our data into two parts. The first half will take the values, lower values, and the second half will take higher values. Then we run two different regressions and calculate our F statistics. And after creating our F statistics, we'll check our F statistics. If the calculated value is high, if the calculated value will be higher than the tabulated value, then we reject the null hypothesis of homoscedasticity in this test. So let's generate a variable, that is generate g income. I'm giving the name g income, and it is equal to income. So here the new variable has been created, it is g income. So it has all the values from the income. Now the first step is just to sort out the data. For this purpose I have to select this. Then here here are some menu buttons, so I'm just going to use the menu button here. Sort. So our data will automatically be sorted here. So it is sorted now. Now I'm going to remove some values from the middle. So I am removing 18, 19, 20 and 21. For remove any value, first we have to select the edit button. So it will take in the edit mode. So views will come in edit mode. Now here's the button delete. So whenever you try to delete any value in your distribution, it's better to choose delete observation and move subsequent observation up one. It will remove the value and take your values up one level. So now 19. So I'm going to delete 19. The same way 20 and the 21. So let's check how many values we have now. We should have 36 values. Here it is. We have 36 values. Okay. Now we run the regression on first 18 values. For this purpose, we use the quick estimate equation and write the relationship here: food expenditure, intercept, then G income. And at the bottom of the page, you can see here's the sample. So we can give the sample range here, and I'm going to give 1 to 18 because I want to use 18 values, first 18 values. So the EVs will take first 18 values automatically. So I'm just going to press OK. So the regression has been run, and you can see here on 18 observations. Now the second step is just to save the sum of the square residual, this value. So for this purpose I am generating a scalar variable. Scalar SSR1 is equal to @SSR. This is the function @SSR which gives the uh, SSR of the last regression run. So you can see here SSR has been created. Let's check the value by our regression. So it has the value 50056.76 and our regression value is 50056.76. Now I'm going to run the regression on last 18 values. So just go to quick estimate equation and once again write the same: food expenditure, intercept, G income. Now this time we have to select the values from 19 to 36. Now press OK. So our second equation has been run here, and the same way we have to save the sum of the square residuals in our second variable. So I'm going to create second variable scalar SSR2 is equal to at the rate SSR. So here we go, SSR2. Let's check the value. It is 178.136.00. So 178.136.0. Now we have to create our f value, f calculated value. So for this purpose, I am going to generate a scalar. But before calculating our f statistics, we have to standardize these two SSR values with their degree of freedom. For this purpose, I am creating another variable, that is a scalar f calculated scalar f calculated 1 is equal to SSR1 divided by, here we have 18 observations, so if we calculate degree of freedom, that is n minus 2, so we have to use 16 as a degree of freedom for first iteration. Similarly, the same way we have to calculate the second value. So scalar f calculated 2 is equal to SSR2 divided by 16. Now calculate f value. So scalar f calculate is equal to f calculate 2 divided by f calculate 1. So here we go. We successfully calculate our f value. So let's check. It is 3.5586. To compare this value with tabulated f value, we have to generate f tabulated value. For this purpose, I am again generating another variable, scalar variable, that is scalar f tabulated is equal to q f distribution. This is built-in function we use automatically gives us, so we can just calculate this. The first one is in the syntax, the first one is level of significance, so 0.95. Then degree of freedom, so degree of freedom for the nominator, and then degree of freedom for the denominator. So for the nominator, our degree of freedom is 16, and for the denominator, our degree of freedom is 16 as well. Here f tabulated. So let's check our f tabulated. So the tabulated value of f at 95% rate of significance with 16 degree of freedom is 2.33, and our calculated f value is 3.558. It means the calculated f value is higher than the tabulated f value at the same degree of freedoms. So it indicates that we can reject the null hypothesis of homoskedasticity in this data set. So it means our data have some problem of heteroskedasticity. Fagan Godfrey test, and usually we can say BPG test. So in this test we use we get the residuals, then estimate the variance, then we construct the PI, this standardized variable, then we run our regression on PI, then obtain ESS, and if the calculated value of this test exceed the tabulated value of chi-square test, then we can say this distribution has heteroskedasticity. Now we're going to check heteroskedasticity through Bush-Pagan-Godfrey test. For this purpose, we have to run regression first. For running regression, let's write ls food expenditure intercept and income. Now we have regression result here. As a second step, we have to calculate the no we have to run the uh, squared residual as a dependent variable. So we do it ls residual square intercept then income. Now so we have to calculate, now we're going to calculate chi-square value. So for this we are going to generate one variable, that is a scalar variable, and chi calculate is equal to, so the we can just multiply the r squared to our number of observation so that we can get chi-square calculated value. We have 40 observations. So this is our calculated value of chi-square. Now we're gonna calculate tabulated value of chi-square. For this purpose, we are going to generate another variable, that is scalar chi tabulated is equal to, in the red, q chi square, and we are taking 95% significance level, 0.95, and 1 degree of freedom by default. Now we can compare our both values. So the tabulated chi-square is 3.841. However, the calculated chi-square is 7.384. It means BPG test also confirmed that our distribution has the problem of heteroskedasticity because calculated chi-square value is greater than the tabulated chi-square value. We can use another test for testing of heteroskedasticity, that is White's general heteroskedasticity test. In this test, we estimate the equation by running ordinary regression. Then we take the residuals as a dependent variable, and at the independent variable we take all x variables and their squares and their cross products. If the calculated White's statistics greater than the tabulated chi-square value, then we can say there is heteroskedasticity, and we can reject the null hypothesis of homoskedasticity. It is quite easy to calculate in eViews because eViews provide this function automatically. So we can easily calculate this through eViews. So we are just going to check our model through White's general heteroskedasticity test. For this purpose, we first need to run our regression. So let's run regression. ls food expenditure intercept and income. Now we got the result of regression here. As the second step, we just go to view residual test and White's heteroskedasticity cross-term. Just click this. Now we can see this is our calculated value of White's heteroskedasticity test. So to compare this value with tabulated chi-square, so we have to calculate our tabulated value. For this purpose, just define a variable, that is scalar chi tabulated is equal to rate q chi-square, and we are taking 95% level of significance with 1 degree of freedom. So we successfully created variable. So let's see the value. So our tabulated value is 3.84. So once again we can see here our calculated value is higher than the tabulated value of 3.841, and it rejects the null hypothesis of homoskedasticity. It means our data are distribution plagued with heteroskedasticity. So let's see what kind of remedial measures we can take. If we know the sigma, then we can transform our OLS to GLS and to handle the heteroskedasticity, because we just use the WLS in the form of GLS, because it is consistent and it is efficient rather than OLS being inefficient in the case of heteroskedasticity. So we just start with the basic model and divide through by the standard deviation. We just divide the whole equation through standard deviation, and we can directly use this through White's general heteroskedasticity consistent error provided by the views. So let's see how we can use White's heteroskedasticity consistent standard error. Just run the regression first. So ls food expenditure intercept then income. Now just go to estimate window, and is a tab button that is options. So just click that, and you can see here heteroskedasticity consistent coefficient covariance. Just check it and click OK. Now it is White heteroskedasticity consistent standard error and covariances. So just freeze this to compare our earlier version of regression and name it equation 2. Okay. So now here's equation 1. So if we compare this standard error from both of the regression, so in the first one where it is not standardized, so the standard error of intercept is too high, that is 43.410, and in the second regression when standard error is standardized it becomes 27.467. It means it is quite consistent. So according to Iqbal, remedial measures when sigma is unknown, so we have to assume that variance of UI is directly proportional to the independent variables. Then we transform our model by dividing the whole equation with the square root of independent variable. On the other hand, if we assume that variance of UI is directly proportional to the squares of independent variables, then we should transform our model by dividing the whole equation with the independent variable itself. So in order to estimate variance, we first use the log transformation of the our regression model. So let's start through quick estimate equation, and here we give our log of e head square, the intercept, then log of income. So here we got the alpha and alpha 2. Now we can use the forecast command to predict our value. So here sigma hat. Now just press OK and statistics. So here we have both the alpha 1 and alpha 2. So we can now transform our GLS on the basis of this estimated value of variance. Alternatively, we can do the same through our command line. So just run the regression for us. So just go to quick and estimate equation. Here log of E hat square, then intercept, then log of income, just press OK. So we got the regression result here. Now we are going to generate two series. The first one is series, and we can also use the generate command. Sigma 2 hat is equal to exponent C of C is a use for the first coefficient plus coefficient 2. So the system will directly give the second coefficient here, then the log of income. So here you can see sigma 2 hat has been created here, and it is now we're gonna create our another series that is sigma hat, and this series will be the square root of the sigma 2 hat. So just series sigma hat new is equal to great square root of sigma 2 hat. Now here another series has been created, that is sigma hat new. And this series is same as the sigma hat. You can check these two by freezing. So this sigma hat we created through the forecast function, and the sigma hat new has been created through the command line. So there's no difference between these two. So in order to solve the problem of linear probability model, we use the generalized least square instead of ordinary least square. For this purpose, we use the code.wfi1. So let's open the file. We have already opened the file. So let's start by running our regression. So just go to quick estimate equation and write the equation here, dependent variable, then intercept, then an independent variable, display Coke, then display Pepsi, just press OK. So we got the regression results here. Now you're gonna forecast. Here we can write P hat. So just click the statistics. Now we create the series where the probability is less than 0 or where the probability is greater than 1. So this is the main problem of linear probability model. That sometimes it goes beyond the sometimes the probabilities goes beyond the 1 and less than 0 bound. So let's create the series plt0 is equal to p hat less than equal to 0 and another series pgt1 is equal to p hat greater than equal to 1. Now we will check how many of the observations are having the probabilities greater than 0 and probabilities greater than 1 and probabilities less than 0. So we'll just create the scalar NLT 0 is equal to 0 sum PLT 0 and the scalar for greater than 1 and GT 1 is equal to 0 sum PGT 1. Now we check our two scalar variables. The first one is the observations having greater than 1 probability, so we just check the NGT. So it has 0 values. Now we're gonna check those observations having probabilities less than 0, so that is 16 observations we have. Now we're gonna truncate the non-positive value of p to 0.01, so by using the p term. So let's do it. So we are going to create another series, that is series p turn is equal to 1 minus PLT0 static p hat plus PLT0 static 0.01. So the series has been created here where just truncated 2.01. So now we're going to run the regression on our estimated variance. So we just run ls p turn static 1 minus p turn, then intercept, then the independent variables. So this is our generalized least square estimates after doing that. So if you see, here's the variance of the probability linear probability model is pi1 minus p. So this is our, so we use this as our variance. So now for the second set of our GLS estimates, we omit those observations where probability is less than equal to 0. So just go to estimate and right, cook, C, then dependent variables, and here we can write our command, or so we can give any condition if we like, if p hat greater than 0. So it means the system automatically take those values where p hat is greater than 0. So the probability is greater than 0. Otherwise, system automatically reject these values. So let's run our regression here. So and this is our weighted regression of Coke model. In the end, we would like to thank Professor Dr. Kim Sang-Hoo for his guidance, Professor Dr. Javed Iqbal for using some of his slides in this presentation, and we would also like to thank the audience for their kind patience.